Okay, so this is the second lesson on refraction. Here we're going to learn Snell's law and how to calculate the angle of refraction. So let's turn our attention to the wave fronts coming in at a different medium as shown by this diagram. So we have a ray coming in at an angle theta I, and it's going to refract at some angle theta r relative to normal. So the easiest way to derive the equation for how theta r relates to theta I and the two different media is to look at the actual wave fronts. And we're going to make triangles on here that will give us some we'll use some geometry to use that. So the triangles are going to be pretty small. So the first triangle is going to be the triangle that is where one side is the actual wavelength in medium 1, then the length of the boundary to the point where the wavefront intersects the boundary, and then we have this side right here. The key thing to understand from geometry, if this is theta I right here, then this angle right there is also theta I. Okay. Now when we have the refracted ray, we have a theta r, and in that medium we have another wavelength. So if I draw a triangle where this represents the wavelength right here, lambda 2, okay, the refracted angle here is the same angle as this small angle right there. Again, you can use geometry to verify that for yourself. But we have our two triangles that share a common side. And for the first triangle right here, this length, the red length here, is the wavelength in the medium. So we can see, if we do a little derivation down here, if we take the sine of theta I, right, that's going to be equal to lambda 1 all over that common side, which we'll just call x. And we see from the triangle made by the refracted waves, we see that sine of theta r equals lambda 2 all over the same wavefront, or triangle length, excuse me. And if we divide the two equations, then we see that the sine of theta I divided by sine theta r equals lambda 1 over x divided by lambda 2 over x, which is nothing more than lambda 1 over lambda 2. And if you recall from our previous lesson, lambda 1 over lambda 2 is the same as n2 divided by n1. Okay, so we see a nice important relationship that the ratio of the incident to the refracted angle, or at least the sine of the ratio of those two, is equal to the ratio of the two indices of refraction. Put another way, we can write this as n1 sine theta 1 referring to usually the incident angle, but the angle from the medium which you're starting, equals n2 sine theta 2. And again, n2 is the medium in which you're entering, theta 2 is the second angle, which is generally the refracted angle. Before we do an example, we can see a conceptual way of looking at this that you need to be aware of. So in this first case, let's say we are starting in N1 where it's air, and this is, let's say, water, such that N1 is less than N2. N1 is 1 and N2 is 1.33. We can see that because N1 is less than N2, if I solve for the sine of the refracted angle, sine of theta 2, N1 over N2 is less than 1, I am going to get, that means that the incident angle has to be bigger than the refracted angle. In other words, if N1 over N2 is less than 1, this needs to be bigger such that than this in order to get an equality here. What that translates to is anytime you enter a greater index of refraction, your refracted angle is going to be less than your incident angle, or put another way, the refracted ray bends toward the normal. Okay, so you got to be familiar with the term bending toward the normal. And one way to look at that is if I follow the original incident ray, it wants to continue along that straight line. And I'll put little dots there. And we see that the refracted ray is deviating toward the normal. It'll never bend past the normal, but it will approach the normal as the incident angle increases. Using the same logic, if we enter a medium where it's a lower index refraction, in other words, we reverse this ray, where it's starting in water and enters air, we see that it refracts, and we see that the theta I is greater than theta R. I take that back. The theta R in this case is greater than the theta I when we reverse it. So when you enter a lower index refraction, in other words, your initial is greater than your second one, then the refracted ray bends away from the normal. Okay, so the rest of the problems are really just variations of using Snell's law or looking at various refracted rays and understanding what the relative index refraction is based on whether it bends away or toward normal. So so in our first example, we're going to look at this general diagram, even though it's messy, where we have an incident angle of 60 degrees. We're starting in water. We're going to enter an oil. In other words, a higher index refraction. We want to know the angle of refraction. So we can use Snell's law. We can say N1 sine theta 1 equals N2 sine theta 2. All right, N1 is the initial 1.33. Sine of 60 equals 1.75. Sine of the refracted angle. Make sure you are in degree mode, and if we punch in the numbers, we get sine of theta R equals 0.658. So if we do the inverse sine of that, we get that theta R is 41 degrees. And since we're entering a higher index refraction, we expect this to be less than the incident angle. It's bending toward the normal. Now what if N2 was air instead of oil? So we would have, starting in water, sine of 60 equals 1 times the sine of our refracted angle. So we would have sine of theta R equals 1.15. And if you do the inverse of that on your calculator, you get an error. Right? And this is not a mistake on our part. You cannot take an inverse of any sine of anything greater than 1. So why are we getting an error? Well, that's telling us something interesting physically, which we'll look at later. Okay, so this concludes the lesson on Snell's law. You'll have more practice with this in class and as homework.